Hello. My name is Asbel Fontanes. My partner is Abdul Garmish. Um, they couldn't be here, so I'll be presenting the project myself, or lab one myself. So to first start off, just to show the timestamp, um, everything was last modified 10/5/2020 these say today just because I've opened the file to show the presentation, but everything was last changed around Monday, Saturday. As you can see, the 4th and the 5th are Sunday and Monday. I'm assuming anything that says the 9th is just because I have the file open currently. So to first start off, here's my half adder, or my team's half adder. We decided to first start off with using structural Verilog to program our gates. Um, Basically exactly what the professor showed. I don't see any reason to show any schematics for this because the schematics is in the lab manual. But basically we just take, for the half adder, we just take the XOR between A and B and store it into sum, which is then outputted. And then we take the AND of A and B and we output it to C out, and that's what gets outputted from the half adder. For the full adder, then we have the inputs A, B, C in, sum, and C out. Then we used wires W1, W2, W3. And then what we do is we pass wire 1 as the output for our first add. We pass W2 as our second for our C out of the first half adder, and then we pass A and B, and we do the calculations there. And then we connect the W1 or the sum from half adder 1 to the B input, and then we connect A to C in. We take the sum of that, and then it comes out as the sum and our C out, which is wire 3. And then to assign the official C out, we take the OR between the C out from our first add and from our second add to get the C out of everything. And as you can see, we used behavioral Verilog here for this full adder, just so that we could get some experience with half adder and full adder. Some experience with structural and behavioral Verilog. And then the next thing is our RC adder. So we have two 3-bit inputs, A and B, a mode, which is a 2-bit input, and then we have an input C in, another 3-bit input, which is our sum, a 3-bit output, which is our sum, and then our final output, which is C out. To do our RC adder, we had to use 3 full adders since it's a 3-bit number. So we had to use 1 adder for each bit, 1 full adder for each bit. So what we do is then we pass the first bit to our first adder with wire 0 and sum 0. So what you would get as your sum from adding the first bit with the second bit is going to go to your first bit in your sum. And then what we did, so that we could take a hold of adding and subtracting numbers, is we take 2's complement by just XORing it with mode 0. Since when mode 0 is 0, your even parity is going to allow you to stay with the same number, but when mode is 1, you'll get an even parity that is then flipped of B naught of B, which allows you to hold with that. I think that's one of the best things that we did here. It just allows us to optimize the code as much as possible, instead of having to do any if statements or anything and then use 6 adders instead of just 3. And then what we do is we take the the C out from your first bit because that's your carry out. You put it as the carry in of our second bit. And then we do the same addition again, putting it to the first bit in sum, and then we take the carry out from here and put it into our third bit. And then our final carry out is C out. And then the addition between these two bits is the sum will be equal to the sum of the second bit. And then for our ALU, what we did was we basically had same inputs as the RC adder and outputs. We had a wire for our T sum or temporary sum and a wire for our temporary C out. And then we passed all that into our RC adder to hold the temporary sum and the temporary C out of the addition of those two pins and the mode and whatnot. And then we did logical evaluation or equate a logical assignment. So if mode equals 0 or mode equal 1, set sum equal to our temporary sum. And we can do it this way just because mode already takes the hold of adding and subtraction. So we don't need to worry about changing it. Then we have mode 2, which is equal to A XOR B, and then we have mode 3, which is equal to A and B. And then we have our default value, which will be 0. And then we assign C out for mode 0 and mode 1. It's going to have an actual value of temporary C out. For any other value, we have it equal to 0 just because we don't want any previous what's it called? Any previous calculations to carry on to when we're doing AX or B or A and B, since AX or B and A and B doesn't evaluate to C out or anything. So we just decided to always set it equal to 0 as the default, which allows us to do everything we need to. So then to go to our simulation files, the first thing we tested was our half adder. Let me open that. So we can see we have our registers A and B, our wires for our outputs, sum and C out. We run it through the half adder. We do 100 time steps and then finish. So we first set A equal to 0, B equal to 0, B equal to 1, A equal to 1, B equal to 0. If you would like, we can just run the simulation real quick. Cancel. Sorry. Forgot to set that one as top. So set as top. And then if we run that simulation again, run behavioral simulation, we see that if we take 1 and 1, we'll get 0 as our sum, and 1 is as our carryout, which makes sense because 1 plus 1 is 0 in binary, but you'll get a carryout from that. And if you do 0 plus 1, you'll get 1, and you'll get 0 in your carryout, which all makes sense. So that's that. And then if we look at the let's stop this simulation. So if we look at the full adder simulation, once this is done, closing. So full adder test bench, we can see that we have, just set this as top, just for when we get to it. So what we see is we have A, B, and C in as our inputs or registers, and some C out as wires for our outputs. And we run that through, and then we just continuously flipped at different time steps each single value, and we just initiated it all at 0. So if we run this behavioral simulation, and we zoom to fit, we can see that everything makes sense. A plus B. Let me just zoom in a little bit more. Let's bring this over here. Let's drag this all the way to the front. So we see that when we have Cn equal to 1, sum is equal to 1, which makes sense. When we have Cn equal to 1 and everything else, when we have B equal to 1 and everything else equal to 0, we get a sum of 1. When we get B1 and equal to 1, Cn equal to 1, we got a 0 here and a 1 as our carry. Same thing for when A is equal to 1 and everything else is equal to 0, we get a sum of 1. When we have A equal to 1 and C equal to 1, we get a carry, which makes sense. And then the last important one is when we have ones everywhere, because 1 plus 1, we should have a carry plus another 1, and we'll have a carry plus a sum. So everything looks right, everything looks good. So then if we continue on to our RC adder task bench after this closes, and I'll just close up some of these files so that things go nicer. So now if we look at our RC adder test bench, set as top, and open it. Sorry for that. Oh, why aren't you opening? Oh, there we go. Okay, so we have our register 3-bit A, B. I don't know why I set mode equal to a 3-bit. That should have been a 2-bit. I don't know why it didn't give me an issue. So I'll just fix that real quick. Shouldn't be a problem. Register 1, 0 should be good now. Yeah, I really don't know why that didn't give an issue when I tested it, but it worked previously. If anything, I'll just actually leave it how it previously was. But you can see that I know that it should have been with a 2-bit instead of a 3-bit. So if you run this code, run simulation, run behavioral simulation, if it gives an error, I'm pretty sure it's just because of that mode being a 3-bit when it's supposed to be a 2-bit. But we'll just try it to see. Yeah. So the video smart enough to fix that for us. So when we're in mode 1, 5, 1 should give us 4 since that's subtraction. And when we have 5, 1, we should get a 0. 5, 1 in mode 0, which is addition, we got 6, and that's correct. I only really tested this with a handful of numbers, one at a time, just to make things easy, but we can see that it's working. And like I said, RC adder should have had mode equal to 1, 0. To a 2-bit instead of a 3-bit. I don't know why it works. I'm assuming it's just that the video is smart enough to realize that that we only care about the first 2 bits of mode instead of the 3 bits that it has. So if we look at our final test case or our final test bench, which is the ALU, let me just go ahead and close everything else. We can see that we have the register. See, I had mode as a 2-bit here. Anyways, so we have A, B as 2-bit registers, C in as a register, and our wires, which is a 3-bit sum and C out. And then here's our initiation of it. And then we have 100 steps, and then we just flipped through a couple of different test cases to see if everything looked right. So if we run a simulation, run behavioral simulation. We'll see that, oh, sorry, I set the wrong thing as top. I was like, why does the simulation look wrong? It's just because we didn't set the correct thing as top. So let's just go ahead and set the ALU as top instead of the RC adder. So if we run the simulation now, run behavioral simulation. There we go. I don't know why it didn't start previously. And just let it do its thing. The video can be a little slow sometimes. So now if we look at this, yep, we're running the ALU. So we have 7, 7 at 0. That's adding, which makes sense because 7 plus 7 is 14, which you have a 6. And then the carry out would be equivalent to 2 to the 8th, which is, or not 2 to the 8th, sorry, 2 to the power of 4, I believe. No, 2 to the power of 3, sorry, 8. So 6 plus 8 is 14, which is right. So 7 minus 7 in mode 1 is 0. 7 plus 7 XOR is going to be 0 since because of even parity, they have 1s and 0s in the same place. So you'll get 7. 7 and 7 in mode 3 will give you 7 just because they have 1s in the same exact place. So if we do the same thing with 5, 2, we see that 5, 2 in addition gives us 7. 5, 2 in subtraction gives us 3. 5, 2 in XOR will give us 7 again. And then 5, 2 in AND mode will give us 0. So yeah, that's everything for this. That's the ALU, that's the RC adder, that's the half adder, and the full adder. In the next portion of the video, I'll just be showing how the FPGA works and everything, just because it takes a while to run synthesis and all that to make sure just to get it to the board. I don't know if you want to see me running the synthesis. I assume not, since all the tests and everything work correctly. And then what is it called? Just to show again, this is the file location of everything. So if we go to, sorry, not there, here, that's the same file path as up here. So the dates look right. Like I said, I'm pretty sure the reason why this says the 9th for these files are just because these are all affected by every time you open the project. But if you actually go in and look at the source files, you can see everything was modified between the 3rd and the 5th. Nothing past due date. And then in the simulations, everything was updated between the 4th and the 5th, except the RC adder, which just happened now. You saw me do it, you saw me modify it. That's why it says the 9th, but everything should look correct. If not, feel free to let me know, and we can talk it over. But that's going to be it for the actual program of it, and I'll be showing you the FPGA on the next portion. The FPGA part, testing the code on the board. As you can see, this is the exact same file path that you saw prior. So let's just go ahead and program the device with the ALU code. So if we program, and now we come to the board, let's turn everything down just to start fresh. So if we were to pull up 1, we get a 1 bit in the first position. And if we were to turn on B1, we would get 2, because 1 plus 1 is 2. So just to quickly reference what each pin means, so this is A0, A1, A2. This is B0, B1, B2. This is C in mode 0 and mode 1. So you just saw that the addition works. So let's go into subtraction mode by putting mode 0 up to 1. So right now you'll see all 1, 1, 1 because of 2's complement of B. But that's just flipping bits. To do the full 2's complement, you have to turn C in up to 1. And now we see that our sum is equal to 0 and our C out is equal to 1. In a future version of this code, we would have probably thrown out C out in subtraction mode, just because the C out really has no
actual representation of anything in subtraction. So if we were to turn this up to 3, right, and we were to turn on B0 up to 1, we would see that in subtraction we would get 2, which makes sense. So if we were to turn A up to turn A up to 6, right, we would then get 5 as our input, and if we were to turn this up to 7, we would get 6 as our output. And then if we were to then go into our AND mode by putting M1 up to 1, we would see that the only ones that are ANDed are 1. And if we were to go into our XOR mode by turning mode 0 down to 0, we see that we get an XOR in positions 1 and 2 in sum, which makes sense because if we have A0 on, A1 on, and A0 on, A1 on, and A2 on, and we only have B1 on, the even parity will happen between these two. Sorry, every time that I've been saying even parity in this video, I've actually been meaning odd parity. Even parity is when you're talking about not XOR. With XOR, you actually have odd parity. So every time you have an odd number of ones, you will have a 1 come out. That's what I actually meant. I'm so sorry for saying even throughout the video. So just as a point, XOR is odd parity and NOR XOR is even parity. So yeah, that's that. And that's basically the FPGA. And that's it's actually pretty cool to be able to do this and have my own FPGA board. So thank you. And if you have any further questions, feel free to reach out to me or Abdul. Thank you so much, and have a good rest of your day.